Morning, everybody. Hope you had a nice weekend despite having to take the test and did find time to relax. As you can see, it's raining here in my garage. Um, I was up in Big Bear this last weekend and I got caught in a rainstorm that lasted about an hour, but was like a real rainstorm, and realized how much I miss the rain. So I thought we'd have a little rain today. Anyway, okay, well, you took the test, and as I thought, you did pretty well. The average was 80, so at this point, the curve will be kind of a standard 80 to 90 would be a B range, and 90 to 100 A range, and 70 to 80, 70 to 79 would be C range, although we're not assigning grades. And so you may have seen on the Canvas site, or you might have gotten an email that posted the letter grade ranges as applied to your scores. Again, this is nothing formal. We do not apply letters now to the midterm. That's just a way for us to give you an idea of how you're doing. What we do at the end of the quarter is after you take the final, we add up your total points, see how you did relative to the rest of the class, and then apply letters. And of course, we will be applying minuses and pluses and all that sort of thing. But what's posted now is just to give you a general idea of what your grade would be if you continue to do the same on the final as you did on the midterm. Okay. So many of you did really well. Boy, there's a bunch of you that did not do so well, and I'm not sure what to tell you. I imagine those are the folks that are not coming to class. Hopefully you're watching the video. And you should know that if you are concerned about your grade, the first thing you should do is contact Chuan. Well, the first thing you should do is actually, I think now, if I believe you can see exactly what you got wrong. I believe that was available to you right after the test. Canvas is new to me. I will go back and check that to make sure that you can see what you got wrong, which questions you got wrong. And if you have questions then after that, like if something is confusing to you as to why you got a question wrong, of course, look up the answer in your notes in the book. But if you're still confused after why you got the question wrong, contact Chuan, your TA, and she will help you with specific questions and that sort of thing. And if she has any questions, of course, she'll contact me. But that's one of her jobs, is to help you go over your exam if you have any questions on why you got something wrong. Okay. I really, that would be the first thing to do if you want to improve your grade for the final, is go over the questions one by one that you got wrong on the midterm to make sure you understand how you got it wrong, what you did wrong. And then hopefully you know that, if you're unhappy with your grade, that you'll have to study more. As I said, despite the fact that this is being open book and people really, no matter what I say, people come in not studying. You absolutely have to study, and hopefully if you didn't do well, you're convinced of that now. There's some folks that got in the 60s and the low 70s I'm concerned about, but hopefully you do have to study. Those are probably folks that didn't listen to the advice, so hopefully you'll do better on the final and you'll get a passing grade in the course. Okay, let me take a few minutes here. I imagine there are going to be some questions, and you can either speak up, raise your hand, or put them in the chat. Okay, questions on the exam or the grading. Don't be shy. I mean, I'm open to any sort of questions here. I know often after the test, people have concerns, and I want to make sure I help you as much as I can here. Nothing. I got a few questions through email about what type of curve there will be. And as I said, because people do pretty well on this type of open book exam, they got the average was 80. That's a B minus. That's pretty much no curve is generally applied in this case. I guess if people do much worse on the final, then there would be a curve that would shift things a little bit. But this will give you a sense if you do the same on the final that you did in the midterm. You can imagine your grade would be what's projected now. Okay. Good. Here's a question. I was hoping for one. The answers, okay. Thank you, Bonnie. I'm really glad you said that. The exam answers are hidden on my end. I will absolutely make them available later today. As soon as, I finish class and have a little lunch, I'll go on and figure that out. Again, I apologize. I thought I had set that to be available as of Monday, but if they are still not available, I will check that. No, sorry, Jacqueline, there's no possibility, as this says, there's on the syllabus, there's no extra credit in a course like this. I'm sorry. You can just, I'd be happy to help you, and I'm sure Tuan would be happy to help you study for the final so you do better on the final if anyone's not happy with the way they did on the midterm. We are here to help you do better, to study and do better on the final, and that will bring your grade up, certainly, if you do better on the final than you did on the midterm. But there's no extra credit, I'm sorry. Cool. Other questions about the exam? Or how things are graded or anything like that. I understand this can be a little bit of a deceptive course because, it is straightforward in the sense that, you're hearing stories about people, but there are concepts that you're learning. Whether sometimes it might not seem like that because we're telling such really cool stories about these interesting individuals who have these perceptual skills. And you think, oh, it's just a class full of kind of stories and interesting anecdotes and stuff like that. But there are concepts deep down, and it is a college course, a UC course, so you do have to learn. And you'll see today's lecture is going to get a little bit more technical, but hopefully not overwhelmingly technical. But it's important you study, the details. The questions are designed to make sure you've understood the concepts of the actual class content. That's not just like memorizing, individual lines on slides and stuff like that. But it's important that you think about why these concepts are the way they are, why the brain, why the perceptual system is the way it is. So many of you did very well, but for those of you that struggled, that may be part of what happened too. Okay, other questions? All right, good. Also you had what, 18 out of the 60 questions? You had answers for 18 of the 60 questions. So most of those questions I think were answered correctly. There's some folks that didn't seem to gain an advantage by having answers to those questions for some reason. I'm not sure what to do about those students. I'm actually giving you answers to the exam in class. If people aren't getting those answers right, I don't know what to do. Okay, then let's go back. If things come up later with the test, after the break or something like that, I'd be happy to answer them. But let's go back now and continue where we were talking. And we started talking about this new topic that will be tested on your final, which is about touch. There we are. Okay, let me just fix things over here a little bit. Cool. Cool, there I am. Nice. All big. Good. All right. Excellent. So we were getting kind of a running start on this by meeting this really fascinating guy, John Bramblett, who's a blind painter. He lost his sight, as you know, later in life, well, later being in his early 20s, and decided to take painting up at that point. And we learned a lot about his technique, how he paints through touch. And this is a nice story to kind of get us into the issue about what happens when we have expertise in touch and how that reveals some really interesting things about how the brain changes with experience. Okay, so this chapter, you'll see, I mean, as I introduced the course, I talked about there were some concepts that we were going to learn that were, kind of, important scientific concepts about the brain. One of them being plasticity, the others being imitation, or what's called mirror neurons, and the final one being multisensory perception. These are all kind of emerging concepts, or actually they're pretty established, but when I was writing the book 10 years ago, they were emerging. Now a lot of research has been done since then, and they're really important concepts in the perceptual field. These might be the three most important new concepts in perceptual psychology. And so we're learning about these concepts, these scientific concepts, through these stories. And actually, those three concepts will now be emphasized in the last half of the course, starting with plasticity. So we're going to learn about what happens when a sense is lost and the other senses compensate for that sense. And this is something we've discussed kind of here and there as we went through and talked about, Daniel Kish and the beat baseball players. We're going to get kind of into some of the nitty-gritty of this now, talking a little bit about the details of what happens in the brain when this occurs. So let's do that. We're going to talk about what happens with blindness and touch. Now, the reason I should mention, I could have really talked about this kind of cross-sensory compensation with pretty much any chapter, but I decided to save it for touch when I was writing the book for a very practical reason. And that's because at that point, at least, most research on cross-sensory changes in the brain, say with blindness or deafness or anything, was done on people's skill with touch. And for that reason, I decided, let's put this in the touch chapter, because I think this really kind of not only does a great job of explaining this cross-sensory kind of principle in the brain, when one sense is lost, the other ones kind of help make up for it. But it also kind of demonstrates how great our sense of touch can become in instances where we really need it. Okay, so let's talk about this. It was known for a while before 2010 that individuals who are born blind have a better sense of touch. They have greater touch sensitivity, and in some ways they have major changes in sensitivity, so that a person, when they're, I don't know, say 75, if they've been blind all their life, they will have the touch sensitivity of somebody who's 50. So your touch does go down. You probably know this from your grandparents. They'll talk about it sometimes. Their sense of touch does decline, something that's going to happen to all of us. You're able to feel things in your old age and all that sort of thing, but you're not quite, your skin isn't quite as sensitive when it comes to touch. You might know a little bit about this when it comes to the elderly having more falls, falling down more often. Of course, that can lead to broken bones, broken hips, that sort of thing. And the reason for that, at least one of the major reasons for that, is because of a loss of kind of sensory feeling in the soles of the feet. Okay, probably have heard this, that older folks don't quite have the touch sensitivity in the soles of their feet, so they sometimes have trouble basically feeling the ground, and that can, between that and some loss of coordinative skill, that can lead to many falls. People kind of just walking around their house and falling just because of that loss of sensitivity. However, for the blind, it turns out that their sense of touch is substantially better. And so, somebody who is 75 and would normally have a degradation in their sense of touch, if they've been blind all their life, will have better touch sensitivity and have better touch sensitivity in the soles of their feet. So that reason for falls would not be as prominent in the blind. Of course, being blind, there's other reasons for falls, but that's interesting. By the way, there's in experiments of touch sensitivity, what they'll often do is, do I have anything around like that? Yeah, here's a little guitar pick. I don't know if you can see the guitar pick, but what they'll do is they'll put like little probes on the skin, and I'll show you one of these devices. I have a picture of one of these devices. The question is, how much pressure do you need to notice the probe on your skin? If you've got, say, a probe that has two little points, how far do those points need to be away for you to feel them as 2 points? And as you get older, it becomes harder and harder to perform those skills accurately. So this is how they can test touch sensitivity. And often, it is often these days done with the feet because of that known practical concern. But it's also done with the skin of the hands. And in fact, a lot of the research leading up to, say, early 2000s was done on touch sensitivity in the hands. Okay, so yes, the blind have a better sense of touch than the sighted when it comes to touch on the skin, say, of the hand. Why would that be the case? Well, as you can see there's a little image of somebody touching Braille, and I'm sure you know what Braille is, right? You see it all over the campus. There's signs, most of the signs to classrooms and restrooms and directions in our buildings have Braille translation under them, right? And Braille is a series of raised dots that you feel with the tips of your fingers, and it allows the blind to read, right? So in theory, that could be the reason blind individuals, especially blind individuals from birth, would have a better sense of touch because they have this practice at touching Braille. That's certainly what I thought when I was looking into this research. Okay, so maybe that's it, right? So that experience with Braille kind of heightens their sense of touch, and that's why a majority of blind individuals have a better sense of touch than sighted. I was wrong by that assumption, okay? And I think a lot of people would be wrong by that assumption, would make that assumption and be wrong because very few blind individuals actually use Braille. And when I wrote the book, that was 10%. And I bet you it's closer to 6-7% now. Because, okay, years ago, it was the only way the blind could the major way the blind could read, right? There were some books that were read and recorded. Sometimes newspapers would be read and recorded so the blind could have a newspaper, through sound. But it wasn't that common. It took a lot of time and a lot of money and all that sort of thing. Now right, that with Siri and Alexa and all these other kind of talking computer systems, that you can get a completely new document read to you with a computer voice. So even though people still learn Braille to some degree, it's not nearly as necessary as it was. So I would say less than 10% of the blind actually use Braille these days. I would say it's closer to 6-7%. There's some advantages to learning Braille still. It allows kind of for a multitask. You can listen to music while you're reading rather than have the book read to you or the newspaper read to you. But most folks don't bother learning Braille these days because they aren't as dependent on it as they were before computers could speak. Okay. But what that tells us, even back then, that this general improvement in touch sensitivity, okay, which was true of the vast majority of blind people, the Braille experience couldn't account for it because very few of those folks that had the better touch sensitivity actually used Braille. So what else could be responsible for that? And that kind of realization led into the idea that something is going on with the brain even without that intensive touch practice. Okay. And that's what led to the idea of cross-modal plasticity. So this is a term I've been kind of casually throwing around that talks about this compensation when one loses a sense, right? Now, you should know that just the big picture here is going to be that this happens when one loses a sense early in life or late in life, as we now know, okay? And it doesn't even need to be a major loss like total blindness or total deafness. Cross-sensory plasticity, so the ability for the brain senses to kind of make up for each other when there's something lost in a sense, okay, is kind of a general strategy of everybody's brain. That's where we're going with this. It's not just something for the blind, not just something for the deaf, although that's how it was first understood. Now we know it's true of your young, healthy, good senses brain, and everybody else's as well. Because there's research showing that even if there's little degradations, right? You'll like this. I don't know how many of you wear glasses. I can't see you, but if you're nearsighted like me and you wear glasses versus contacts, okay, I have a little bit of a better skill with some aspects of sound than I used to when I was younger and didn't need glasses. So even the small degradation that occurs, and glasses will correct the middle, but I have a degradation in my sight to the side here because I have glasses, not contacts, right? And that small degradation is enough for my brain to say, hey, who can help Rosenblum with his fuzzy vision on the side? Hearing, can you help with that? Can you help tell where things are? And hearing will say, yeah, sure, I can help with that. And even that counts as cross-modal plasticity. We'll see other examples of that where, if you're blindfolded for a short amount of time, you can start seeing evidence that the other brain regions will try to help out, right? Which is cool. So this is not something specific to the blind and deaf, or people like we used to think that we're either born blind or born deaf, that this is only the time we actually see this. Instead, it is something that is a general strategy of everybody's brain. Okay. But let's go back to the blind, because I think those are the most instructive, understanding that, kind of a very severe loss to understand this. So when we touch something, all right, those of us that are sighted, typically what happens is we light up a part of our brain that's on the side. Okay, so it's the touch region. Now, let me show you on my head. Remember, I think I mentioned this to you guys. I can't remember if it was this quarter or last quarter, because I taught this class in the spring too. I'm thinking that I'm gonna maybe get my head tattooed so you can see the brain regions, remember? Because, I'm not gonna grow my hair back. That's not gonna happen. So I thought, I got a tattoo on my head, and some people, get fancy things, images of sailors and their mother or whatever, but I'm thinking of actually tattooing a brain on my skin. And I'll let you know if I end up doing that. I told my wife I was thinking of doing that. She thought it was a terrible idea. Anyway, so right here, if I were to do that, you'd see a kind of an outline right here on the side of my brain. Hopefully you can see that okay. If nothing else, I should have my kids draw a brain region on my head with a marker or something. Right here, you'd see that would be what's called the touch region underneath there, of course. It's kind of a little strip that runs down here. And when I touch something, okay, you would see this area lighting up. Now, what's really cool about this, and this is something that's helped scientists understand how the brain is responsive, is that the body is actually mapped out here. And that's what's being shown in this image right here. Yeah, you can see. So what you're looking at here is kind of the brain from the front, okay, not from the side, but from the front. And, if you were looking at that little strip, you could look through the other regions and get right to that little strip. You would see that the leg is represented towards the top here. And what else do we have here? The nose. Wow, there's a lot of region for the nose, isn't there? Especially, I imagine, especially for my nose. And the tongue gets a lot and that sort of thing. And then there's other parts that get a little bit less, that's what you're seeing here now is if the body or actually had the size of its limbs and face and skin, depending on how much was devoted there to those parts on the brain. This is how it would look. Really, it's just another way of saying that the amount of region on the brain, on the touch strip of the brain, is dependent on the sensitivity of that part of the body, right? And therefore its function to some degree. So you have a lot of touch sensitivity on your hands, and there's a big region on that little sensory, that touch strip that's devoted to the hands. You got a lot of sensitivity on your tongue and lips and your face and all that sort of thing. Same thing. You have much less on like your lower torso and at least the majority of your legs. You have less sensitivity there, so there's less region devoted there, okay? So that's what happens when we touch. We light up different parts. I touch with my hand, I light up the part that is representing my hand. I touch with my nose, I light up that part. Okay, that's what happens for most of us. Okay. For the blind, something else happens. Okay. Now, I said that, again, cross-sensory plasticity is a general strategy for everybody, but it's going to be a strategy that's used when it's needed. For the blind, okay, right, because a blind person can't see, they're going to actually increase their touch sensitivity by using the region of their brain that isn't being used, right? So when one loses their sight, even when there's a little degradation in sight, there's less of the visual brain used for sight, which allows the visual brain, the now kind of unused visual brain, to help with another sense. And in this case, we're talking about touch. So if one goes blind, their sense of touch increases largely because of the use of the region of their brain that's not being used. In this case, the visual areas. Visual areas, by the way, are in the back. You know that if I had my tattoo, right? How did we know that? Well, we've known that we had a sense of that for a while, I can say. We had an idea that that was the case, because what you'd find is sometimes, people that did know Braille, that 10% that actually knew Braille, if they knew Braille all their life and they were very good with Braille, and then they had a stroke, right, that affected the visual areas of their brain, right? Okay, so there's a brain lesion and it happens in their visual areas. Okay, they're not seeing anything anyway, so there's nothing to affect visually, right? But they would lose their ability to read Braille as well if that brain lesion, if that damage was in the visual area. Okay, they'd be spared for other things. You could have them touch other things with their hand, and they'd be sensitive to things like textures and that kind of that probe thing. How many probes are touching your skin now? That sort of stuff. They'd be fine with that, but they would their ability to read Braille would degrade severely. Right? They'd still be able to kind of make out things, but it would take extra effort, suggesting that a lot of their touch is done in the same places that it is for sighted folks. But there is a special type of touch that is occurring in the visual areas that aren't being used for vision anymore. Okay, that's what's suggested. Right? Now, here's something cool. You live in an age where you can actually do experiments on, quote, brain lesions. All right, what does that mean? With humans. We now have a technology that can create a very, I would say, mild and very brief lesion in the brain. It's not really a lesion. It's kind of just a way of stopping the brain's activity in a specific area. And it is called transcranial magnetic stimulation. Now, this is going to become one of your best friends over the next few weeks. Transcranial magnetic stimulation. And what you're seeing here in the bottom image is the device that's used to basically break a part of the brain for a very brief duration. Okay, and it's connected. This little device here, it's connected to an arm that can allow these little mouse ears to go all around the head, and that arm is then connected to a device that can allow these mouse ears to actually send out a strong magnetic signal to a part of the brain. And it can do it in different ways, as we'll learn. It can send it out in one big signal, like that, or it can send it out in little pulses. Okay, right now we're going to be talking about the big signal one, because what that does is it just shuts off a brain region. It doesn't even shut it off. It actually kind of just suppresses a brain region for a brief amount of time. And then the brain says, okay, I'm back online, and then working again, and it's fine. It lasts, maybe, less than half a minute or something like that. But it is functionally a way now where you can, kind of find out what regions of the brain are responsible for what types of perceptual functions. which is really cool. So now what we can do, rather than waiting for somebody to have some damage, some permanent or very severe damage to the part of the brain to see what's affected, we can essentially do this experimentally. We can shut off parts of the brain and determine what it affects, what perceptual function it affects. Okay, so let's just do a little review here. I'm going to abbreviate this more frequently as TMS, stands for transcranial. Your cranium is, just your skull. Magnetic stimulation, that's TMS, okay? And it induces a lesion that's transient, just meaning it kind of just shuts off or at least suppresses activity in an area of the brain just for a short period of time. That's all we're saying to it. Okay, so now what you can do is you can bring in sighted subjects, you can bring in blind subjects, and you can try to shut off different regions of the brain with this device to see what happens with, say, somebody's sense of touch. Super cool. And I should say again, it sounds a little severe, but I've had this done, and yeah, for a while, for the 20-30 seconds it's active for, it does feel a little strange, but then your brain's fine, You may have heard this in other contexts. It's being considered as a treatment possibly for depression, possibly for addictions, that sort of thing. And I think it's not quite clear how well it works for that. But for research, it's amazingly useful. It really is a revolution in technology for understanding the brain. Okay, so let's do some of this. Imagine you swing over these mouse ears now. Right now, it's kind of at the back of this guy's head, probably targeting maybe the visual areas of the brain back here, okay, back at the back. But now what we're going to do is swing it around, pretend we swing it around, and put it at the side of the head where that little strip is, okay, that is involved with touch. Okay? So what we're going to do is basically shut down or at least suppress the touch regions of the brain. Okay, and when you do that and have the person close their eyes and then kind of swing the mouse ears over and go like that to the touch region, you can target regions pretty accurately. And then put something in their hand, like a shape, a block. Is this a square block, or is it a kind of pyramid shaped block, or is it a rectangle or something like that? When you do that, it's something that would be easy for you to do without this TMS. But when you apply TMS and ask people to make those discriminations, they have a terrible time with it. They say, I'm not sure. I feel points, so I guess it's not a sphere, but I can't tell if it's a square or a pyramid or a rectangular shape or whatever. I can't do it. Say, okay, put the block down. And then they move things away, so it's no longer affecting the brain. And then they ask them to do it again, and they say, oh yeah, no, I can tell it's that pyramid shape you were telling me about, that sort of thing. But while that TMS is being applied, it's not working, suggesting that that part of the brain is in fact used for some sort of shape discrimination. Cool. All right. Now, what happens if you apply this to a blind person the same way? They're going to have the exact same problem. Okay, you're going to find that they will also, so you're bringing the mouse ears around, it's affecting the side of their head under which is that little touch strip of brain, right? They're going to have the same problem. Okay, they're going to have the same problem. But unlike the sighted folks, if you instead target the visual brain areas, okay, if you bring the mouse ears back around to the back of the head where it is right now in that picture, and turn it on onto the visual regions, and then ask them to hold the shapes, they'll say they're able to do it. They're able to determine what the shape is, but it will affect something else. It will affect fine touch discrimination, the type that might be used for Braille, whether they know Braille or not. They now have trouble kind of, determining how many dots are in a line on that raised piece of paper. They don't need to have known Braille, right? It could be these could be non-Braille sorts of textures on the dots, right? That's formed by the dots. But they will lose their sense of fine touch discrimination. And that won't happen with sighted folks. suggesting that certain types of touch in the blind are processed with the same areas that are used for sighted folks. But when it comes to fine-grained touch, detailed touch, like I'm trying to think what else we could talk about besides Braille, like keys. Sometimes you're able to tell which key is which while you're kind of feeling it in your pocket, right? Sometimes you can tell which coin is which. If you have to say, I need a quarter for the laundry, rather than pulling out your handful of change, you can kind of put your hand in your pocket and feel which is a quarter size and which has the ridges around it and all that sort of thing, right? That type of fine-grained discrimination is better in blind individuals. And now we know through TMS that it's probably better in blind individuals because they're able to use their visual brain areas that are no longer needed for vision. Okay. So that's a wonderful way of kind of showing that there is this cross-sensory, cross-modal or cross-sensory plasticity that occurs with the blind. And it seems to involve the blind brain making use of its visual areas to help touch, but a specific type of touch, fine-grained touch. Okay. It's a great example. Okay, one thing I should just say very quickly, I just noticed this. When I say cross-modal or cross-sensory, I mean the exact same thing. So if you want to take a note on that, I think I tried to use cross-sensory on the slides now, but this might be from a leftover from an old slide. It means the same thing. The modalities of the senses are, the five senses. We sometimes use the term modality in the field, but cross-modal and cross-sensory means the exact same thing for you. Okay, just a little clarification there. All right, cool. Let's continue. And let's talk about an interesting experiment. And this is going to now really address the issue of the fact that cross-sensory plasticity is a strategy of all brains, not just the blind and not just the deaf. Okay? Because it happens relatively quickly. So I alluded to this experiment before when we were talking about taste. This is an experiment where sighted subjects, typically undergraduates who want to make some money, okay, volunteer to come into a laboratory, or I think it's often done in maybe a hospital room or something like that, and agree to be blindfolded for 5 days. Okay, it's a serious blindfold, by the way. It's not just a scarf around your eyes or something like that. They really make sure that you have no light vision whatsoever. It's a good solid blindfold, right? It's comfortable, but yep, vision is completely shut off for 5 days. All right, cool. People are made comfortable. They're given a lot of money. They're made comfortable. They have things to do. They can listen to music, listen to audiobooks, whatever. They can socialize, all that sort of thing. They're made as comfortable as possible. The reason, by the way, I brought this up very briefly when we were talking about taste, just to remind you of this, is because one of the first things people notice after they've been blindfolded is that when it comes time for their first meal, food will have less flavor than it typically does, right? Remember, we were talking about this fact when we discussed the dark restaurants and how important sight is to actually experiencing food's flavor, right? Why I think that when these restaurants say that this is a way for you to experience flavor without distractions, they're actually taking something out of your experience of flavor. And that's, supported by these kind of self-reports of people saying, yeah, I didn't think it would affect my sense of taste when I was blindfolded, but there you go. It absolutely does. That over the course of those 5 days, they might start enjoying food a little bit more, but it does take a while for the other senses to come in and help out. But that's just an anecdote that I wanted to remind you about. Okay, but here's what's going to happen. There's going to be a lot done with these folks. They're going to be earning their money. One of the first things they do when they come into the lab is they are put into a functional magnetic resonance imaging device. So this is just the device that allows for pictures of the brain and really kind of, videos of the brain to be taken as, different tasks are performed. So we've talked about this before, and these are some images. These might be CAT scans, but it doesn't make a difference. These are images of the brain from these the functional magnetic resonance imaging device. What they do is they first kind of get a baseline of what people's brains look like while they're just sitting there, and then they get another baseline, which is of what happens to a person normally when they are touching things. Okay, so they'll have them touch raised dots. Okay, and it's like Braille. I mean, for all intents and purposes, we could say it's Braille, but it's made a little bit easier for these sighted folks. Basically, they'll touch two patterns of raised dots. So it is exactly like this. They're little raised dots on paper. I think this is actually real Braille, but it's close enough. It's fine. They make it a little bit easier, as I said. But they'll touch two patterns of raised dots on paper and be asked whether they're the same or different. And some of them are going to be more challenging than others, right? Don't forget, they're completely blindfolded. But the question is, can they perform the task? And most importantly, what happens to the brain when they're performing the task? Okay, and this is done on the very first day, right after they're blindfolded. And so they look at what the brain is doing at that point. Cool. All right. Now, okay, let's pretend you're the ones that are in this experiment. Cool. You're going to be making your money. You're getting a lot of money. Let's say they give you $1,000. Okay, this is worth it then, isn't it? That's a lot of dough. The next thing is that you're going to have, across that 5-day period, big time lessons to become better touchers, basically, Braille lessons. For all intents and purposes, again, it is Braille, but you're kind of taught to recognize patterns and discriminate patterns and things like that, right? And, you're in a hospital room, there ain't a whole lot of other things to do. You listen to music and stuff, but, now here's your task. You're going to earn your $1,000 with your blindfold on and try to get better at recognizing these raised dot patterns, okay? And then after every session, they have you come into the functional magnetic resonance imaging device again, and they take videos of what's going on in your brain as you're performing the test. So basically, they're retesting the fMRI, the functional magnetic resonance imaging, scans and images of your brain while you're performing these discriminations. And what they're interested in seeing is whether there's changes as you've practiced over the 5 days, certainly. Okay. Until your very last day. It must be exciting when your blindfold's coming off, you get your $1,000 and you can go back in the regular world. They do it again, okay? And they do the fMRI again. They scan your brain, but they also do something else. They apply our new friend, transcranial magnetic stimulation, as you are doing this, okay? And they're going to apply it maybe unsurprisingly, to the visual areas of your brain. Basically, they want to see if your brain has changed the way a blind person's brain has changed, okay, except over the course of just 5 days. So here's what they find. It's a very well-known experiment and one that's been replicated many times. Here's the results. So, discrimination of touch induces activation of the visual brain regions. Okay, so that does happen. So at first, when you touch these raised dots the very first day, okay, you're just basically causing activation in this strip along the side of your head. But as your practice goes on, as the days of being blindfolded go on, you start to show activity in the visual regions. Okay, so that increases over the 5 days. In other words, you start seeing this cross-sensory, cross-modal plasticity. So you're finding the unused visual regions of your brain willing to help out with touch. and they're used more and more across those 5 days. Very cool, right? As I told you, yes, this works with the blind, but even being blindfolded, sighted people being blindfolded for 5 days start to show this compensation. The poor visual areas of your brain saying, I got nothing to do, I mean, I'm getting no light whatsoever. Anybody need help? And the touch areas go, yeah, they're subjecting me to this 5-day training of this ridiculous raised dot discrimination. Can you help with this? The visual area goes, I'm happy to. I'm bored as heck, right? That happens. Okay. All right. Okay, let me just make sure I've got this. I want to make sure I got all the logic here, right? Just give me a second. Yes. I didn't mention that there's another group of subjects down the hall from you, okay, that are actually going through something similar, but guess what? They're paid less, I hope. They're in the hospital room for 5 days. They go through the Braille training, but they're never blindfolded. Lucky them, right? They're making, say, $500 for the 5 days, right? You're making $1,000 by being blindfolded, okay? But the question is there going to be a difference in how the brain is used depending on if you are blindfolded or not? You would expect this. However, both groups now are going through this intensive Braille training. They're a group that is also going through 6 hours a day of this Braille training. Okay, are they going to use their visual brains to help out? And the answer is not nearly as much. It is greater for you if you're blindfolded. If your visual areas are basically not doing anything, then you see much more involvement in touch than if it is occupied with vision. Despite the fact that the requirements for touch for both of these groups is the same, 6 hours of Braille training. If you're still able to see things, your visual brain will become much less involved with that than if you're blindfolded. Okay, that's what it's meant here, is greater than for the Braille trained only. When I say Braille trained only, this is a group that is trained 6 hours a day in Braille, but are not blindfolded. They're still able to see. Okay, all right. Now, here's something that you're going to find a little surprising. There's another group of subjects on the other side of the hall. And this group is blindfolded for 5 days, but is not given the Braille training. They are asked to do the Braille discrimination when their brains are scanned, but they do not have to go through 6 hours a day. Instead, they listen to audiobooks for 6 hours a day. They don't have this intensive touch training. And guess what? Just by virtue of having been blindfolded for 6 days, their visual brain gets as involved, okay, with touch as yours did, even though you were doing your 6 hours a day of Braille. So being blindfolded only without the touch training still gets your visual brain areas involved in touch. It really has to do, it seems, with that visual area saying, I want to help out, I want to help out. And even if the touch area goes, well, I'm not doing anything special this week, right? It's not doing that 6 hours a day. Visual areas will say, I still want to help, give me something to do. You say, okay, you deal with fine-grained touch, right? And so you don't need that 6 hours of training in order to get your visual brain involved. They turn out, that group down the hall that didn't get the training, they turn out to do as well with the touch discrimination as you did, despite having your 6 hours of training. That was really surprising to a lot of folks, right? That you would think 6 hours of training would really help your discrimination, but being blindfolded, in both cases, my case, their case, seems to be the trick. That seems to be the trick. And, okay, when the TMS is now applied to my brain in the visual area, right? My skill is reduced, which is not surprising now that we know that the visual area is helping with touch. But that is true of my group, right? Which is the 6 hours of Braille training a day and being blindfolded, as well as that stinking blindfolded group down the hall who luckily didn't have to go through the 6 hours of training a day, right? hopefully they get less too, less money too, right? So the Braille training isn't really what allowed the visual areas to come in and help. It's just being blindfolded, which I think was really surprising to a lot of researchers. So visual deprivation allows your visual brain to enhance your discrimination, okay? To enhance your touch discrimination, right? Yeah, you might, with 6 hours of training, I imagine you could learn to recognize some Braille or something like that. But when it comes to sensitivity of touch, and when it just comes to saying this is the same raised dots as this is, right? That group down the hall is going to do just as well, and their visual brains are involved to help out just as yours are. It's the blindfolding that seems key, which is really interesting. Okay, we're going to talk about this in just a second and talk about how your visual brain actually gets involved with touch in even faster cases of visual deprivation. But I think this would be a good time to do one of our polling questions. So let's do that. Okay. All right, we just talked about this on the 2 slides ago or so. What is the main reason that most blind individuals have better touch sensitivity? A, their use of Braille. B, their touch brain can be reassigned to vision. C, their visual brain can be reassigned to touch. Or D, both A and B. Should be very straightforward. Go ahead and look at the previous slide, or is it the previous slide? Yeah, just the previous slide. But I think you'll get this right. Okay. All right, I'll give you another 10 seconds or so. All right, let's see how we did. Most of you did get this right. The correct answer is C. But we'll go through this because not everyone got it right. Okay. If you look past, on our past slide, the slide right before the one I finished just now, you'll see that certainly it's not because of their use of Braille. So, the vast, almost every blind person is going to have a touch sensitivity better than sighted people, and only 10% of blind individuals actually use Braille. We talked about that. Next, their touch brain can be reassigned to vision. Okay, well, that's not true because they're not able to see, so nothing's going to be assigned to vision, right? They're not going to, assign a part of the brain to see better because they are blind. But what happens, as I talked about in the previous slide and this last slide that I just went through, is that the visual brain that's no longer being used for sight can be reassigned to help touch. So the correct answer is C in this case. And some of you answered both A and B, but that's not correct. As we said, Braille's not the reason. And it's the visual brain that's being reassigned to touch. All right, go. Oh, sorry, I didn't share the results. Sorry about that. There you go. There you go. So you can see most people got it right, but there are a few didn't. So take a picture and we will stop sharing. Cool. All right, let's continue with our discussion then. So We see with 5 days of blindfolding, a sighted person's brain starts acting like a blind person's brain by showing that there's a shift in what the visual brain areas usually do, and to help out with touch. And we also saw that it is really the blindfolding that helps, much more so than any sort of practice in touching, right? This sort of thing occurs just by virtue of an area of the brain no longer getting input. You got to give, our brain areas are really very ambitious when it comes to this sort of thing, right? The visual area could say, this finally I get a rest. I've been, spending my whole life processing visual images. I'm going to take a rest now. But it doesn't do that. It says, I'm not getting any input. I need to be doing something, so I'm going to help out touch, even if there's no touch requirements that are any more challenging than what usually occurs, even if you aren't asked to do that 6 hours. Okay, cool. Let's go on and see cases where even less deprivation is needed for this to occur. Okay, so your visual brain is ready to help you touch. So with shorter term deprivation, much shorter term deprivation, you can see enhancements in touch by the involvement of the visual brain. So this is now not 5 days of blindfolding. This is 3 hours blindfolding, which sounds a lot easier to do, right? You sit there for 3 hours, and typically in these experiments, people are listening to music, they're chatting with other people who are blindfolded, right? It ain't terrible, 3 hours, and you're going to make some money, I assume. And you're told just to kind of sit there with your hands relaxed on the arms of the chair or something like that, or maybe crossed. What they want to make sure is you're not kind of practicing touching things or anything like that. They just want you blindfolded, right? And what you find is after 3 hours, okay, there's an enhancement of touch. You become more sensitive just after 3 hours of blindfolding. Now, just to give you a tiny bit of detail here, I doesn't have to be this particular demonstration, but I wanted to give you another example of how they test touch. It's not going to, in this case, be of raised dots like Braille. Instead, they use a device that's often used in research and sometimes with older adults to test sensitivity. It's basically a little plastic grid. It's hard to, this image kind of shows it, but we should get some photos of it. I've played with these before. It looks like this from the side. It's actually a circle, and it's about the size of a fingertip. So here you actually see these ridges being applied to the fingertip. And in these sorts of experiments, subjects are asked to say whether the ridges of this plastic grid are following kind of the length of your finger, or are they going across the width of your fingers? Basically, is this plastic grid, maybe I can show you this. Oh, here. Make me big. Yeah. Is this plastic grid going the long way on your finger, the long way on your finger, or the width way on your finger? That's it. Okay. And then what they can do is they can manipulate the plastic grids in different ways. They can make these ridges deeper or more shallow, or they can kind of very carefully apply different amounts of pressure. These are all very comfortable, it's not like your finger's going to get hurt or anything like that, but how much pressure would be applied in order for you to actually detect that difference. If it's barely touching your skin, you might have a hard time. If it's pressed a little bit more, you'd have an easier time. The question is, if there's a change in your sensitivity to make these, judgments of straight or sideways sorts of grid patterns after you've been blindfolded, and the answer is absolutely. And again, these are subjects who are not practicing touching anything, right? They're just sitting with their hands maybe on the arms of their chair straight up, right? There's specific controls to make sure they're not practicing touching the chair or their clothing or anything, right? But their discrimination of touch is improved just by virtue of being blindfolded, which is so cool. It really, really is cool. The visual brain, it's got nothing to do. It's type A personality, right? And it wants to help, and it absolutely does help in this case, right? And then there are other situations in which it's thought that the visual brain actually gets involved sometimes with touch if it's a very specific type of touch, even while sight is available. Okay? So this example I've been giving about touching your keys in your pocket or touching coins in your pocket, when you are doing something like that, that kind of very fine type of touch, it's the case that your visual brain is probably getting involved to at least some minor degree. Hold on a second, sir. Yeah. So finding objects by touch, when there's very fine discrimination, maybe the best example is, I have some, I wish I had my keys here, but I have some of those like little, plastic or rubber things around the top of some of my keys, so I can determine, which key is for which when I, want to go to a lock. It's a long story, but where my band practices is not the greatest part of town. This is true of a lot of rehearsal spaces. They kind of tuck them in, places in town that aren't great. And sometimes there's, folks outside that are, that look a little intimidating. I mean, I've never run into trouble, but there are times where I've wanted to just get into the rehearsal space as quickly as possible. So the key I have to that building, I put a little rubber thing on it so I can put my hand in my pocket, know exactly which key that is, put it right in the lock and get right in, right? When I'm doing that, when I'm feeling around in my pocket for that particular key with the little rubber thing around it, I'll bring it in later for you. I think you know what I'm talking about, right? You can buy these at the hardware store, right? I feel for that key and I know this is the key. It is very possible that I actually am using my visual region just a little bit to do that. So spatial touch, finding objects by touch, it is thought that this occurs. Why? Because when you ask people to do these sorts of tasks in a laboratory and scan their brains, you do find that their visual brains can get involved. It's not like being blindfolded. I mean, you see much more involvement over even the course of 3 hours when it comes to the visual brain's ability to help with touch. But you do see a little bit of it. And if you, do a TMS of that area, when I'm trying to find that key, it's probably the case I'm not going to be quite as good, right? So even in those cases where, we used to think that the visual brain areas just were responsible for vision and they didn't do much else. Now we know that, yep, it helps blind people. It helps when we're blindfolded, even for 3 hours. And it might help even when we're not blindfolded in very specific cases of touch, which is interesting. I think the big take home here, the important story here, is that cross-sensory plasticity, this thing we've been talking about, cross-sensory, cross-modal plasticity, is a strategy of all of our brains. It's something that our brains are always ready to do and probably are doing a lot more than we realize, even without major sensory deprivation. Yeah, I guess you can, call that, when you're just feeling, when you can't see something that you need to find that's very specific and has a lot of detail in it, like finding a specific key in your pocket. It is kind of like being blindfolded in that you can't use your vision for something you would usually use vision for. When you're touching something, with that type of fine brain detail, your visual brain probably gets involved. It's not just the sensory impaired. Okay. In just a few minutes, I'm going to be talking about some of the neuroscience behind this. Okay, what goes on during plasticity? All right, what happens to cells? How cells change their patterns of communication? But before we do that, I'm going to give you a kind of cool example of this plasticity that I think you'll find very interesting. So it will probably, what time do we have here? Yeah, okay, we'll probably get to it in a few minutes before the break, but I was thinking I could give you a break before we get to that tough slide, but let's try to get to it before the break. But before we do that, I'm going to talk about a device that has been designed for the blind to make use of what's known of cross-sensory plasticity. So this is a device that actually, it's these type of devices have been in development since the 1950s, but this is one of the more modern incarnations of it, where a visual scene is translated into touch stimulation. Okay? I say you can taste scenes because in this case, the touch stimulation is applied to the tongue. And there's reasons for that. I was just, my editor said you should, name these sections in a kind of provocative way. So what does that mean? Taste scenes, what does that mean? What it really means is that there's a way of translating something visual to something tactile or something touch. So it doesn't have to do with taste really. It has to do with the fact that in this case, the touch is being applied to the tongue. And that's what you're seeing right here. You're seeing this little kind of, I don't know, this little square. It's about the size of a stamp that has these little electrodes on it. And that is put onto the tongue. And these electrodes kind of apply a very subtle type of stimulation. So I've actually played with this. It's kind of cool. You put it on your tongue, and what you end up feeling with these little electrodes is kind of I don't know, kind of like bubbles on your tongue. It almost feels like fizzy bubbles or something like that, but a very kind of specific pattern of little bubbles. And it's not like soda bubbles that are, they feel a little bigger in your mouth, I think. It's more like champagne bubbles. If you've ever had champagne or fake champagne, the bubbles kind of feel smaller and in more precise locations. It feels more like that. Okay, but they're, they kind of stay in one place. It's not like they get to part of the tongue and they pop or they move around or something like that. They're in one place. And the question is, can stimulation like this be a substitute for vision? Now, as I said, these sorts of systems have been in development since the 1950s. In the old days, they would have like this huge thing. I remember seeing one of these types of things in my dad's office that was kind of like a vest that you would put on your back and then close it up in front. And on the back, there'd be like little vibrating posts, and that would touch your back, all across the back, from the top of your back down to the bottom, across the side. And then there'd be a camera attached to this. And the idea was you would move around the camera as a blind person. The camera would take in information of the scene in front, and then that information would be translated to little vibrations in the posts that were on your back. And it would be a pretty literal sort of form of stimulation in that, say, you're moving around the camera and on the wall there's an image of a triangle, a big triangle. So this would be for like testing or training purposes. Okay, so you move the camera and you point it towards the wall and you said, okay, there's a shape there that's been pasted to the wall there, that's on the wall, and that shape is now going to appear in vibrations on your back. Can you tell what it is? And so all of a sudden on my back, there would be the little posts, it's an array of posts, would form a triangle, and those little posts would be the ones that were vibrating. And I would, basically feel stimulation of a triangle on my back. And the question is, am I going to be able to determine that's a triangle? And actually, people are able to do this okay, both blind folks and sighted folks. It got dicey when, things were a little bit more complicated than just a triangle or a square or a circle or something like that. If you were to use this in a real world situation, you'd have to deal with three-dimensional objects. You have to deal with objects that might be in front of you and that might, be something you could trip on. Could you use this well enough? And people with lots and lots of training could use it okay. But oh my gosh, this was such a heavy thing, right? I remember this was really not something you'd want to wear for more than maybe an hour a day or something like that. And in order to get around, they had these giant batteries that would have enough power to kind of vibrate these posts, and it would be a really cumbersome thing to wear and to use. So that eventually developed into what you're seeing there. And the reason why it's on the tongue is because, first of all, those things aren't vibrating. What they're doing is they're just kind of, creating a little, very minor electrical current, right, to your tongue. And the tongue is a really good place for that electrical conductivity to occur, right? I don't know if you ever did this, but when I was a kid, the way we would know a 9-volt battery still had a charge was we put it on our tongue. I don't know if you guys ever did that, but it was it's a kind of a thrill, like, oh yeah, this one's still good, right? Because your tongue is really good at detecting that sort of thing because of all the moisture and everything. So that's why it's been applied to the tongue now. You no longer need this giant vest. You no longer need big batteries. You just need a little bit of current going through. And so you'll now see how this might be usable for the blind to be able to, get around, to traverse cluttered environments like an office by feeling the stimulation on their tongue. And I realized I hadn't set this up for audio and video. Let me go ahead and do that. And then I will show you a video of this, which I think you'll find really interesting. Okay. Oops. Yeah, share sound, optimize for video, and here we go.
At first glance, Roger Bain looks like an independent guy who loves his power tools. And he is. But here's what he's actually seen since he was a young man. But part of his world is slowly coming back into focus through experimental technology called BrainPort. One day it could actually help blind people see, in a sense, using their tongues. Yes, their tongues. It swaps tiny cameras for eyes and transforms the images into electrical impulses that are felt on the tongue.
It's as if it's drawing on the tongue the still image, and so if you capture the images fast enough, paint them fast enough, it's like a video display. Instead of being on a screen, now it's on your tongue.
When you're a kid, I don't know if you did or not, but when you were kids would draw on your back and you try to guess what it is.
In normal vision, the eyes send signals to the middle of the brain. From there, the signals are sent directly to the visual cortex at the back of the brain. Not so for the blind. The BrainPort retrains the way the brain processes information by first stimulating the tongue with an array of tiny electrodes. The nerves in the tongue send signals through a different pathway to the brainstem and the area that deals with touch. Eventually, the blind person learns to interpret touch as sight in the visual cortex. Sounds impossible? Well, watch how Roger walks through the BrainPort office without any guidance. He can navigate this obstacle course, picking out specific shapes.
Excellent.
The camera sees this image, Roger feels it on his tongue, and that's how he can even spot the logo on a football jersey.
Very good.
Other blind volunteers recognize numbers.
9.
It's like learning a language. At first, you might need to spend a lot of time thinking about what the translation is. I may feel stimulation in the right front part of my tongue. What does that mean? But very rapidly, like learning a language, you might learn a few quick vocabulary, and eventually you become so fluent that you don't need to think about it anymore.
Blindfolded, I try it myself. After a humbling first attempt,
I want to say it's diagonal.
Okay. And this one is vertical.
I managed to understand some of the BrainPort language.
I want to say it goes this way.
You are correct.
Okay.
The technology is improving. Today, a car looks like this to a BrainPort user. A few months from now, they hope it will look like this. And in a year and a half, more like this. For the blind, they're a glimpse at more freedom.
This develops where the next generation can really get benefits from it. Even if I don't get the greatest out of it, I'm still can determine if I can see their eyes and maybe even see a smile or a grin, that kind of stuff. It can be cool.
And for the rest of us, it's a miraculous look at how our brains can be trained to rewire themselves. Daniel Seberg, CBS News, Madison, Wisconsin.
Cool. So yeah, this is, oh shoot, hold on. Good. Here we go. This is showing what the device kind of translates into stimulation on the tongue here. This is what they were hoping for. Well, eventually they're hoping for something like this, but if they felt like they could get it to there, then that might be very, very usable. But what's the status of this? Well, this was, when I was writing the book 10 years ago, it, it was about what you saw there in the video. They did start selling it then. I guess it is available to buy, but it has not really taken off. And there's probably many reasons for that. The resolution can only get so good, not because of the number of electrodes here, but your tongue is a very, very sensitive space. Like, I mean, you saw in the that little image of the map of how much area the tongue gets on your little sensory strip here, on your little touch strip here. It gets a lot, so it's a good place. But it's only going to go so far, right? So even if you add more of these electrodes to, in theory, give a better resolution, your tongue's going to come to a point where it just can't, feel the difference between those positions. Okay. But, people can be trained to do okay. You saw that individual do okay with this sort of thing. This is called the tongue display unit. So when you first try it, you are able to maybe get some lines and curves after maybe a few minutes of feedback. And that's what you saw with the reporter trying it, the blindfolded reporter trying it. It takes a little while. With training, you see, as that blind individual showed, being able to discriminate shapes and being able to determine the location and the direction of real objects like a rolling ball. Potentially you can traverse mazes or get around an office space using this device to some degree. And to some small degree, be able to discriminate letters and that sort of thing. But as I said, it's unclear that this is going to be the solution that most blind people are going to want to use. It could be that there are other technologies that I think are probably going to be more effective in terms of actual stimulation of the optic nerve, gene research, that sort of thing, that actually might do more to restore some visual processing in a blind individual. So now they can actually stimulate, the right into the retinal nerve. So there is something like a visual experience with these people that might actually have a better future than these touch devices, but it still kind of gives an interesting window on cross-sensory plasticity, I think. And in fact, one thing you find is that after people have some training, and this is, I think, probably the blind individual you saw in this video had enough training to experience this sort of thing. It's no longer an experience of having just the tongue being stimulated. So imagine you put this thing on your tongue, you're just starting off, and like the reporter did, and you have to feel what's going on the tongue, and then kind of translate, well, that if I could see that visually, it might be a slanted line. It'd be a very kind of conscious translation of tickling on the tongue and what the visual image might be. Very conscious, very, very, exhausting, I would imagine, after a while. But then with practice, people would say, including probably this individual you saw, that you don't start just experiencing things on your tongue, you actually end up experiencing things out in the world, right? It's not like you're doing this conscious kind of effortful translation. That kind of comes reflexively, like a second nature after a while. And you start to experience things that have, a depth to them, right? Not only are you experiencing a line, but you have an experience of it being out there in space. And you're kind of no longer concentrating on the tongue, you're concentrating on what's out there and kind of, ignoring to some degree what the tickling is on the tongue. That's now kind of something that's reflective. Okay, that happens with these folks. That absolutely happens. They all say that after a lot of practice, you start experiencing things outside the body. You're no longer just feeling your tongue tickled. You're actually starting to experience things outside. And when that happens, something really interesting happens. That's when you see the visual brain get involved with this task. So I just think this is a fascinating kind of anecdote, because what it suggests is that there is kind of an experiential sort of involvement or experiential outcome of the visual brain getting involved, right? So at first it's just the tickling and tickling, and since these blind people have never experienced this before, maybe the visual brain wants to get involved, but it's going to take some work. It's not like touching Braille or something like that, right? The visual brain is going to want to get involved. But when it gets really involved, and it's, the visual brain is like consistently being involved in this task, it takes, say, a number of weeks. At that point, does the individual start to feel that things are outside? So the visual brain's involvement in things, in this kind of crazy task like this, actually has this kind of perceptual ramification, kind of an experience ramification, meaning that the experience of the individual changes from feeling just tickles on the tongue, which they're then consciously translating, to actually feeling that there's things in the world, okay? Which is interesting. Well, as I said, these devices, they've only been so good. I don't think there's much of a future for them, to be honest. Maybe other folks would disagree with me. There's still papers that are being written on them, and they are being sold, I guess. I think they're, I don't know if I've had some involvement in the blind community for various reasons, and I've talked to folks about these things, and very few blind individuals I know feel like there's much of a future in this. But okay, maybe when the resolution gets better. But right now the resolution is still pretty poor. So yeah, it's not great. We'll see what happens. It could be that there'll be ultimately there'll be some sort of visual stimulation to the visual nerve in blind individuals that will be more useful for them in terms of aids for the blind, in terms of technologies for the blind. Okay. Let's see here. Actually, I thought I was getting to the tough slide right now. I'm not. Let me do one more simpler slide, and then we'll take a break and then get into the tough slide, I think. Let's see. Actually, no. Let's take our break now. And we'll come back and do a slide and then get into the really tough slide, okay? So let's take our 10-minute break, and I'll see you then. Okay, we're back. Let me just, let's see here. All right. Let me just take a second and see if there's any questions from anybody. If anyone else came up with questions about the test or grading or anything like that, I want to give you a chance to ask before we continue with our lecture. Anybody? No? Okay. If you come up with anything later, feel free to interrupt. That's okay. All right, let's, oops, oh, gosh. Sorry about that. Let me share our screen again. And right there, good. Okay, so wanted to talk a tiny bit more about this cross-sensory plasticity, and actually I'm going to move into now plasticity just within touch. So actually that's really the big point of this next slide I should have mentioned. So we have been talking about cross-sensory plasticity as kind of a strategy, but in introducing cross-sensory plasticity, we've involved touch. Now we're just going to talk about how plasticity occurs for touch itself. Okay, we're not going to be talking about how vision induces touch changes or anything like that. We're going to be now talking about how experience can influence touch. All right, and we know that the touch sensitivity can increase just with the loss of another sense, but you can also increase your sensitivity and your touch skills just with practice, and practice itself can change the brain significantly. So let's talk about that, kind of a different take on this idea. So the more you touch, the more your brain changes. All right. We're going to be mostly talking about touch brain areas. So that's over here again, this is the strip over here on the side of the head, but it's showing you here looking at it from the front. Okay? It's kind of a close-up of one side of the brain, looking at the brain from the front, looking past the stuff that's here so you can see right into that strip that's on the side of the head. Okay, and you can see there's our little map, and this is another way of showing how much of the body is devoted to each of these regions. And as you can see that the amount of body space attributed to different areas of the brain has more to do with the sensitivity of that area and its function in a lot of ways. So look how much area of the brain is given over to the face. Well, we know we have very sensitive touch on the face, and there's good reasons for us to have sensitive touch on the face in terms of being able to control the amount of musculature and stuff that goes on in facial expression and talking and all that sort of stuff. It's nice that we have good sensitivity there, and we have a lot on our hand, not too much on the trunk of our body or on our legs, that sort of thing. Certainly we can feel when somebody's touching our knee or something like that, but our sensitivity on the hands and the face, tongue are much more acute. Okay, but let's talk now about how experience of touch can actually change this map a little bit. We can get more or less areas devoted to different regions of our body with experience. Right. So let's talk first of all about plasticity in the touch brain areas. So as I said, most blind folks don't know Braille, but those who do know Braille and have been using Braille for many, many years do show a change just in the region of the touch brain. So most of Braille is conducted with the three fingers of each hand. So you don't typically use your thumb or your pinky to read Braille. But with certainly your visual brain is going to be involved with this if you're reading Braille, but it does also change the area of the touch brain itself. And what you find is, for those that use Braille, that there's more area given to those fingers that are involved with Braille than there would be for somebody who's not using Braille. So Braille users have a larger area of this map dedicated to the three fingers they're using on each hand for Braille. 3 middle fingers. So I don't think this map is as is specific enough to show which areas are dedicated to which part of the hand. But if you could like kind of zero in more, you see that there are regions in that little brain map that are dedicated to the different fingers. And for Braille users, you see that that was larger for the 3 fingers of each hand than it would be for, say, the pinky and thumb, and certainly larger than it would be for people who didn't know Braille. Okay, that's one way that the brain changes for that sort of thing. There's other, touch specialists besides those that use Braille. So, for example, violinists, have more area dedicated to the left-hand fingers than the right-hand fingers. Now, I'm talking about violinists who are right-handed violinists, and you might know a little bit about this. You've seen violinists play before, right? If they're right-handed, they have the bow in their right hand, and they clutch the fingerboard of the violin with their left hand. So they do this type of thing and that type of thing. And so these 4 fingers especially need to be very sensitive when it comes to, getting feedback for how much pressure is being applied, being able to kind of move the string in just the right way to get what's called vibrato on the violin, right? There needs to be a lot of sensitivity on especially these 4 fingers. Where these fingers are pretty much just gripping the rod. And yes, you need to have, you need to be accurate with your arm and everything, but there's not a lot of specific stimulation going on with these 4 fingers. So there's a huge difference if you were to look at the touch map devoted to the left-hand fingers versus the right-hand fingers. You see a huge difference in the amount of space that's dedicated to the left-hand fingers versus the right-hand fingers. Not just true of violinists, but also true of people that use tools regularly, and all types of tools, right? If you're somebody who puts together cabinets, somebody who has to put together circuit boards, computers, or something like that, you're using screwdrivers and chisels and things like that. And what you find, let's talk about a screwdriver in particular. What you find is somebody who uses screwdrivers often for very precise work, it's almost as if there's a new kind of area of the brain that's kind of devoted to something that's around where the fingers get an area, but it's almost as if it makes a little area for the screwdriver. It doesn't look like a screwdriver or anything like that, but you see that things shift around as if the tool is almost like a new appendage. We're going to talk about tools in a little while and how that, in fact, is true to some degree. A tool becomes like a new appendage. But you see that type of thing in the brain mapping of folks who use tools regularly. In fact, there's an experiment where you can go through training to use tongs. You know what tongs are, like, things you pull things out of the oven with tongs, out of the grill, to flip things over with tongs. You can use tongs to manipulate things as well. And in this experiment, they had people manipulating little rubber corks around a board that had holes in it, and they had to do it, with a certain degree of speed and accuracy. And what they found is after hours of doing this, the touch brain changed to seem like it was actually devoting part of itself to what would really be the tool almost. So yeah, the brain shifts to make room for this new tool, even for folks that have just started this task after a few hours, which is pretty amazing. And also, you find not only does the brain change, but touch sensitivity changes as well. So these first examples, I really have more to do with how the area of the touch brain changes with experience. It also changes how sensitive we are to touch. And here's just one of these probes I was talking about before, this image right here. It's like 2 little, plastic probes are touching your skin. And the question is, how far do these probes have to be away from each other for you to say it's 2 probes versus 1 probe? See, this would be 1 probe. And as you kind of go around the wheel here, the 2 probes start very close together, and depending on your age and where you're touched on the body, you still might say that feels like a single probe until you get kind of around here. Then people typically can say, oh yeah, I feel 2 probes now. But it's a way of testing what happens with touch as we age, or if we've been in an accident or something like that. These are very common in rehabilitation centers and that sort of thing. And they're used in experiments as well. So what you find is people who have years of experience playing piano, they are 2-point touch sensitivity, their ability to tell whether it's one probe, oops, where's my thing? Hold on a second. Yeah, whether it's one probe or two probes just a little bit apart is much better than somebody who doesn't play piano. So it not only changes how the body and the skin is mapped onto the brain, it also changes, functional sensitivity too. Okay, so these are now examples of plasticity within the touch system. Again, I'm using touch as a way to kind of illustrate changes in perceptual sensitivity, because it is where, at least when I had time I was writing a book, where much of this plasticity research was conducted. It was conducted, perceptual plasticity was conducted on touch sensitivity. Okay, I'm now going to give you an example that's going to discuss these changes that this is going to have to do with touch, but it's also going to have to do with motor skill. And the example I'm going to use is, I think, very straightforward and intuitive, and allows me to talk about the actual kind of technical details of how plasticity occurs, how the cells communicate differently with plasticity. This is the horrible slide I was talking about. This is the toughest slide probably of the whole class. It's the most technical slide of the class, but we're going to go through it slowly, and we're going to go through it in a way that's going to hopefully make it intuitive as possible. And what we're going to be talking about is the difference between what's called short-term plasticity and long-term plasticity. So when we've been talking about these changes, whether it's cross-sensory plasticity or plasticity within, just the single sense of touch, you might have wondered, okay, how quickly things revert back to where they were. Let's talk about that in a second. So let's talk about the example of being blindfolded for 5 days in that experiment. And now, because your visual brain hasn't been used for those 5 days, your visual brain is helping you touch, right? It's helping you do that Braille type discrimination, which is evident both through doing brain scans as you're performing the task, and then trying to shut down the visual brain to see if it's involved. And yeah, it's involved. You might have wondered, it's a question I often get in classes, does it stay like that forever? And the answer is absolutely not. You take off your blindfold, you say, yay, I'm $1,000 richer. You go outside and you start seeing the world again. I think they do it gently. So they take off the blindfold in a darkened room and then slowly turn on all that, to make it as pleasant as possible. But after a half a day or so of you looking at the world, things start to go back. And so they have people come in, say 2 or 3 days later, right, after their normal visual life, and you no longer see that much involvement. You might see a little involvement of the visual cortex and touch, but much less than you did right after the 5 days of blindfolding. So the brain then does go back to normal. So those changes that we have been discussing, most of those that involve blindfolding, whether it's cross-sensory plasticity or within touch. Remember, we just talked about being blindfolded and moving around corks using tongs after the blindfold is taken off. That kind of map changes. Those are short-term changes. It's short-term plasticity, right? But we also know there's long-term plasticity. The brain changes pretty much for, ever, all right? It's like riding a bike. They used to say that when I was a kid, you learn the skill and you really have it forever. Yeah, riding a bike when you're first learning is a effortful, kind of conscious, demanding skill. You have to kind of, balance and move at the same time. All kids struggle with it in the beginning. They fall down a few times, that sort of thing. But then after you get it, that's it. I'm going to be able to ride a bike, at least, as long as I'm fit, maybe able to ride a bike forever. Okay. That's a long-term change, right? But the question is, how does this occur? How does short-term change in the nervous system go to long-term change in the nervous system? Let's talk about this. And What we're going to be moving towards here is an example where, that's why I have this keyboard here. People are going to learn a little pattern on the keyboard. These are not piano players, these are novices, but I'll be talking about that in just a second. I kind of want to give you the concepts first, and then talk about that specific experiment. Okay, so what happens when we first learn a new skill? Like, let's stick with, the Braille skill after 5 days or something like that. When you're first learning this skill, there are changes that occur to the brain as we're learning this skill, but they typically revert unless we practice the skill over and over and over again, leading to long-term plasticity. Let's talk about what happens in the brain. Okay. And the way I like to describe this, both long-term and short-term plasticity, is by kind of using an analogy of what happened to an apartment I was renting in Connecticut when I was in graduate school. Okay, it was a bunch of buddies and all graduate students in the same psychology department at the University of Connecticut. We were renting an apartment together. Now, I should mention, this is an apartment that was like an old style house, right? It's not like California, most California apartments are, kind of individual, kind of modern units. This was an old Connecticut kind of, maybe not a mansion, but they had large enough so they had divided it into different floors, and there were different apartments on each floor. So it was old, kind of old style architecture inside and outside. And what happened when we moved in, grad students like to do this. They like to have like parties, and they have dinner parties. They have other grad students over and stuff. And we had a lot of dinner parties. And the way our house was set up is we had the dining room, and then to get to the kitchen, you had to kind of go out in the hallway and make a left and then come back into the kitchen. And to go back and forth kind of became a real hassle until one of us, I can't remember which one of us, realized that behind where we had placed the couch, there was a door there that had been painted shut. Okay, old school, old style house, right? There was a door there that had been painted shut. And we said, where's that go? And then we went into the kitchen and realized it went right into the kitchen. Okay, somebody had painted it shut because they wanted to use that wall for something else. We didn't realize it until we were there for a month or something like that. Say, boy, if we're going to have these dinner parties all the time, what we can do is we can, pull the couch away and kind of, get rid of the paint, chisel the paint away, and use that door as a way of going back and forth between the kitchen and dining room. Cool. That's great. It worked. It was great. And it was much easier to serve food and to get drinks for people and all that stuff. I mean, it was much more relaxing, and it was a good move. That door worked great. And that is kind of what happens in short-term plasticity. As you're learning a skill in short-term plasticity, what happens with the neurons, what happens with the cells in the brain, is they start to use connections between themselves that existed but hadn't really been used either before or for a long time. So what that's called is using connections between cells that had been dormant, that hadn't been used, and starting to use them now, right? And that's exactly what we had in the door, right? Dormant door, basically, right? That door was there. It was a connection between the rooms, but it hadn't been used until we realized that that was something that was going to make our dinner parties more efficient, more relaxing, more fun. So we didn't have to keep on going way outside the room to go back and forth and all that sort of thing. It made things easier, right? Cool. So now what happens when it comes time to practice something for back to short-term plasticity is it keeps making use of that dormant connection, right? You're kind of sustaining it, and the dormant connections become more efficient. In fact, what we did in the house is after a while, we said, why do we have a door there? Why don't we just leave it opened? right? And so what we did is we took the doors off the hinges. By the way, for the most part, we got clearance through our landlord to do all these things. Yeah, we'll talk about some problems in just a second, but we said, let's do this. Let's take the door off the hinges, and now we have a very clear connection between these things. Cool. Made the whole dinner party thing much more effective. That's exactly what happens with cells too, as you practice a skill, right? As you're practicing that cork skill, moving things around, or with a screwdriver or on the violin. Okay, you're using those dormant connections and making them now very efficient to go back and forth. Cool. As you continue to do that, here's something that begins to happen. It gives rise to long-term plasticity in this way. And I'm going to go back to the apartment now. We really loved this door between the dining room and the kitchen. And we said, what if we actually increase the size of the door? So what we decided to do, and this wasn't the smartest thing, but we were young grad students, we actually knocked down a little bit of the wall. Now, we didn't describe it like this to the landlord. And he was surprised when he came in and saw what we did, but we did an okay job. We actually knocked it, we had this big door now that we go back and forth, and we thought, wouldn't it be fun if we could actually pass things back and forth to each other, not just through the door, but through, maybe more of the wall. So we actually knocked out a piece of the wall, the top piece of the wall next to the door. Okay. And now we did a pretty nice job finishing it. So, it was, rectangular, and it looked like it fit into the wall. And then we put like one of those little counters on it. So it kind of looked like, a bar sort of thing. So you could pass things back and forth. The landlord was okay with it after, a little while. Anyway, we created a new connection between the rooms. Because it was so effective to go back and forth through the door, we created a new passageway between these two rooms. And that's what happens when short-term plasticity becomes long-term. It is the sustaining of the doorway, of the dormant connections, but it's also creating new connections between cells. Okay. So by the practice going back and forth, realizing, that we could really make this even more efficient if we put a little window there with a little counter, so we could just pass things back and forth to who wants another beer, that sort of thing, going back and forth. We didn't even have to leave the kitchen when people, wanted beers. We could, whatever, a whole bunch of things that we could do. We created a new connection between those rooms. And now we really had a very, very functional, long-term connection between the dining room and the kitchen. And that's what happens with cells too. As you go from using the existing but not unused connections between cells that then give rise to these new connections that make the connections between cells so much more efficient. Okay? And this is the basis in plasticity in the blind, as we've been talking, and any type of expertise we've talked about this quarter. Okay? When you become a perceptual expert, when you're learning to fine-tune your perceptual expertise, whether it's the taste expertise that Stephen Poe was able to show, whether it's the hearing expertise that the sound engineers and that we've been talking about, you learned about other smell expertise in the book. All of these folks that have established these perceptual expertise had to go from kind of a short-term change in connections between cells to a long-term change in connection between cells. And that's like, practicing hard to ride a bike, riding a bike, now it's there forever. Okay, that's the idea. I don't know. I tell this story a lot, so I don't know if I went back to the house if they ever actually, closed off the space between the two rooms. But I would imagine that, other folks, other graduate students certainly who live there, were going to, like this, and so that's a long-term change in the apartment. Regardless, it's just an analog, right? I mean, it's what goes on in your cells when you learn something for the long term is based on a short-term change between the cells, using again dormant connections that are then reestablished, and then from there going and creating new connections between cells. Cool. Now, to really kind of bring this home to you, I want to give you an example of an experiment I said with this keyboard, and I think this is going to be very useful for you. This has to do with motor learning, but it's the exact same principle. I just use it because it's so intuitive and such an easy experiment to understand. Here's how it works. So we're going to establish a keyboard pattern, and I can't remember this detail of it, but these are individuals who learned, who had no keyboard experience. When I say keyboard, I'm talking about piano. I'm talking about this, this device right here. This is just a tiny keyboard that can be connected to a computer. I have one right over there, but I won't pull it out. Nah, it's not worth it. But you can understand how it might work. Since it's connected to a computer, the computer can evaluate how somebody is learning a keyboard pattern. And the keyboard pattern, yeah, it played a little melody. You would learn to play a little melody, but the scientists were more interested in how accurately the movements were of your fingers as you played the keyboard. And again, nobody had ever had piano lessons in this experiment before, right? This had nothing to do with music, really. It was just a nice way to, evaluate people's learning of a motor skill. Now, this keyboard pattern, I think, was, I can't remember if it was 15 or 20 notes or something like that, that they had to memorize and then learn it over and over and over again, okay? And as it turns out, they had to practice it a lot. They would practice this keyboard pattern for 2 hours for 5 days, all right? And they would come in each day and have their brain scanned. Now, this is, again, this is a motor skill they're learning, but for all intents and purposes, it's going to work fine for us. When I get my brain tattoo on my skull, right, on my skin here, you'll see that this little strip here that we'll be calling the sensory strip or the touch strip is right behind something called the motor strip, which has the same type of map on it. It's kind of a cool way the brain's designed, at least in terms of understanding that we have this little touch strip here that where the body is mapped onto it, and right next to it's the motor strip, and that also has a body map on it, and it's also kind of based on function, not the size of the body part. Very cool. But now what we can do is we can scan to see how the motor part, how the part of the brain that controls motor actions, movement, okay, changes with experience, just like we did with the touch brain. So when I say this is motor learning, this is, learning a pattern of motor actions, like, playing a keyboard pattern. That's what I mean by that. Okay. So here's what these folks do. They come into the lab and they have their little motor area of the brain scanned, and they take note of it, what's where, and all that sort of thing. There's ways you can test for that. And then you have people spend 2 hours in the lab practicing the keyboard pattern that they've learned. Okay, 2 hours is a long time, but they, you're getting paid a lot of money for it, so they take it seriously. They give them a break after an hour, but that 20-note pattern over and over and over again, and then they scan their brains again. Okay, and what they find is, in fact, that the brain map in the motor area devoted to the fingers that are involved in playing the keyboard pattern, in this case it's just the right hand that's playing the keyboard pattern, has more area dedicated to it than it did before they practiced those 2 hours. So that little kind of map where the fingers are represented in that part of the brain now expands a little bit. There's more area devoted to those 5 fingers that learn the pattern. Okay, so that happens after each practice session. The brain organization appears after each session, and the reorganization is just that more area is given to those 5 fingers that are involved, right? Okay, they go home, they have their normal day, right? They come back the next day, and they do a brain scan again. And this is now before the 2 hours of practice, and they find that, nope, everything reverted, right? The brain went right back to where it was before the keyboard it was involved at all in this experiment. right? So what was before showing more area dedicated to those 5 fingers reverted. Short-term plasticity, it reverts if you don't, practice. But then they have them go through the 2 hours again, and they scan again, and they see more area dedicated to those 5 fingers, okay? So the brain reorganization, where you see more of the brain dedicated to the 5 fingers that are involved in the motor task, only shows up after the practice session. Okay, they go home, come back the next day, get scanned before the practice session, it reverts. Okay, practice 2 hours, there it is again. Cool. Come back the next day before practice, reverts again and again. Okay, cool. Half of you are now done with your experiment. The other half of you, I got some good news and bad news. The good news first, you're going to be very wealthy by the time you're done with this experiment. The less good news is what we want you to do is go home and do exactly what you did here in the lab for 4 weeks. Maybe 5 out of 7 days a week, whatever. Maybe they give them Saturday and Sunday off. But most days of the week, you're going to go home and practice this pattern for 2 hours a day. Okay? 2 hours a day. And so that's, okay, half the subjects go home and they practice for 4 more weeks, all right? And the question is, after 4 weeks of this practice, when they come back and will be asked to perform, their 2-hour practice session, will changes be seen actually before they practice? And that's exactly what happens. After 4 weeks of playing this silly little keyboard pattern of 20 notes, let's hope it makes a little music so it's not the most boring thing in the world. They can hear it on the computer, where they're trying to get more and more accurate, right? So the computer can evaluate their accuracy too, give them a little feedback. After 2 hours a day for 4 weeks, they come back and they do a brain scan before they have them actually do their 2 hours of practice. And what they find is that the brain reorganization appears now before the practice session. Right? Their brain, in other words, doesn't need the practice session, the one right there, in order to induce the brain changes anymore. They come in with a changed brain and long-term plasticity. Okay. So basically, you see an example here of short-term plasticity because it's reverting back after 2 hours of practice. If you do this for 5 days, short-term, short-term, short-term. Until with that much practice, it's long-term. It's there functionally forever. If people come back 10 years, will they be able to play the pattern? I don't know, but they'll probably still show evidence that there's more area dedicated. Okay, long-term plasticity is very hard for it to revert. It takes a long, long time. And that's it. That's how, things become second nature to us, how we become an expert at a skill. This skill is very kind of, very, prescribed in the sense that they haven't learned to become expert piano players. They become experts at playing this 20-note key pattern. But it is an expertise, and it's an expertise that is long-term. They come back a week later and they scan their brains, and guess what? That brain is still showing that it's got more area devoted to those 5 fingers by virtue of that much practice. And that's how short-term becomes long-term. That's how, novices become experts. Okay, so the way to think about this, think about it in its analogy with the apartment and kind of going from using dormant connections that are there but are not being used, that painted shut door, then becoming more permanent, the door is taken away, taken off the hinges, then becoming allowing for a greater connections, the new connection of putting that little counter space there, that sort of thing. And it's there pretty much forever at that point, right? There's no way we're going to be able to, even if you wanted to put the door back in, we knocked out that wall. And that's what happens with long-term plasticity. Okay. Any questions on that? Because that is, more technical than we're used to in this class. If this were a psychology major class, there'd be a lot more of this, but for non-majors, I think that's good. It gives you a sense of how the nervous system changes with experience. Okay, then let's go on. Actually, This would be a good place to take a tiny break and do a polling question, actually. Let's do that. It's still raining over here. All right. This should be pretty straightforward for you, I think. Yeah. Okay. I want you to think about this one. This one's going to really test your understanding of that experiment with the 5 days of blindfolding. Okay, so think carefully about this one. I put this one up today because I wanted to make sure that you had the answer to this, because people do get this wrong sometimes. But it's important you understand the concept. After 5 days, which of these subject groups would be able to discriminate raised dot patterns by touch? Oh, best able to. You know something? I'm going to change this question because okay, I'm going to make a executive decision here to change the question, because in that slide I don't talk about performance on the raised dot pattern test as much about brain changes, I believe. Let me take a quick look at this. No one panic. I want to make this as fair and easy for everybody as I can. Yeah, there we go. Yeah, see, that's the thing. I see what I mean. This is absolutely true. The question, the way I worded it, is true. Not only do people start using their visual brain areas, they involve their visual brain areas, but they actually also increase their sense of touch sensitivity. So that changes as well. But I didn't really talk about this as much on this slide. But let me go ahead and do this. Let me talk about how I'm going to change the question. I just want to make this as fair as possible. After 5 days, which of these subject groups will be best able to discriminate raised dot patterns by touch? That's the way I asked it, but I could ask it, and you would probably understand it more if I said, which of these which of these groups would have their visual brain involved to help their discrimination of touch, right? Which would have the most visual brain involvement to help discrimination by touch? A group given 6 hours of Braille training each of the 5 days. B, a group blindfolded and given 6 hours of Braille training each of the 5 days. C, a group just blindfolded for the 5 days without Braille training. Or D, the groups described in B and C would be equally good at discriminating dot patterns. So remember, when I talked about this slide, I talked about there being a group of subjects that were just blindfolded for 5 days and weren't asked to discriminate touch. Remember, what I said about them is, surprisingly, for a lot of folks at least, they did really well. I mean, their visual brain still got involved. Okay, remember I said that? So that should help you answer this question. So I'm going to change the question just a tiny bit, so it's going to say that the visual brain is involved in discrimination touch. So after 5 days, which of these subject groups would be most likely to have their visual brain involved to help them better discriminate touch? That's probably what it would say. Okay, so you can think about it either way, but I want to make sure I refer back to the slide. So don't worry if you don't get this quite. We will explain it and you will understand it by the time we do. Oops. Okay, give me another 30 seconds or so. Yeah, most of you got this. Great. Let me end it here and we can take our time to discuss it. So I don't know why it keeps on flipping back there. Computer's doing some strange things, but we will work around it. Okay, so I'm not going to share the results. The correct answer here, okay, hopefully you guys can see this. It's coming, for some reason, every time I click something on the polls, it switches computers here on me. The answer is D. The groups described in B and C would be equally good or have their visual brain equally involved to help them discriminate these patterns. So the point of this, and most of you got this, it's great. The point is, it really is the blindfolding that allows for this, right? Practice you would think would help a lot, but in this context, it's not so much practice, practice being the touching of the dots. In this context, over the course of 5 days, it really is the deprivation that makes a huge difference. Okay, it's the visual deprivation that then gets the visual cortex involved in helping touch discrimination. So both the groups, a group blindfolded and given 6 hours of Braille training each of the 5 days, does pretty much equally well and it has as much visual brain involvement as a group just blindfolded for 5 days without the Braille training. Okay, so most of you got this right. Good. You get the idea. That's the important thing. All right. Cool. Go ahead and take a picture. I am stopping sharing. Okay. And let's go back to where we were. Sorry, hold on a second. Yes. Okay. Good. Cool. So hopefully you get the general idea here, because we're going to expand on it a little bit. We're going to go back to the situation where we're just talking about not the group that goes home. I think this is right. Hold on, just give me a second here. I've got to check something. Yeah. Okay. We're going to talk about another group of subjects that I didn't mention before involved in the keyboard experiment. Although this time, these are not subjects that are going to go home for 4 months. We're less interested in long-term plasticity. But I think you're going to find this interesting because what we're going to end up talking about is not physical practice, but mental practice. So this part of the chapter is called Neuroplasticity Depends on What You Think. And really what it has to do with is what's called visualization or mental practice. And you've probably heard about this type of thing before, especially when it comes to sports, because that's where a lot of this research, I think, is pretty well grounded. If you've been on a serious sports team, you might have had your coach say to you, if you're, got nothing to do during the day and you're in a car, you're on the bus going to the game or something like that, mentally practice what you do, right? Mentally practice because it's going to help you. And there's pretty strong evidence that if you mentally practice in the right way, say for free throws in basketball or for golf shots and that sort of thing. You mentally practice, especially mentally practicing from your own perspective, it really does improve your performance to some degree. Probably not as much as physical practice, but in some cases fairly close. Because of these, we know this because of these sorts of experiments. So we're going back to the keyboard experiment, which is why that keyboard is there. And what you find is a group of subjects who didn't physically practice for 2 hours each day, but instead mentally practiced after learning the keyboard pattern, they show some interesting results. So, okay, imagine now, this is this new group of subjects where they come in. It's not this 4-week experiment, it's just 4 days in the lab. And what they're going to do is they're going to first learn the keyboard pattern themselves with their fingers, maybe, for over the course of, say, 15 minutes, half an hour. They want to make sure that they're doing it right. And the computer gives them feedback and telling them you're doing it right. Maybe half an hour, okay? That's it though. That's the last time they're going to touch the keyboard. every time after that, instead of touching the keyboard, they will look at the keyboard, which will be in front of them, but they'll have their hands to their sides and they'll just imagine themselves playing that keyboard pattern. They don't touch the keyboard pattern at all. And what you find is, in fact, just by thinking, clearly thinking, and concentrating on doing that, that by the end of the experiment, when they're asked to perform that again, they actually do better. And they show a very similar plasticity as the folks that actually physically practiced. So like the other experiment we talked about just a second ago, you're going to scan them before and after each practice session. And after 2 hours of mentally imagining themselves playing the keyboard as their hands are folded in front of them, right, they end up having the same brain changes as if they had physically practiced and show the same improvements. I mean, people are going to get better at this over the course of 4 days. Even if it's not long-term plasticity, you know, they'll get somewhat better, right? That same improvement in performance of the skill occurs without touching the keyboard. I don't know if it's quite the same, but it is certainly a statistically significant improvement in their practicing, right, in their playing, which is really interesting. And so this suggests that, you know, there really is something to this mental practice thing. And if, you know, it's one thing that it improves your performance, but it actually makes changes in the brain that are at least similar, if not exactly like the changes that occur when you physically practice something, right? So, you know, this is a very real phenomenon. And there's other really cool examples of this, I think. You know, in a sense, remember the rubber hand illusion thing you did? I think it's kind of related to that because, you know, what you're kind of, you know, experiencing can actually affect things in the brain. So there are actually a number of rubber hand demonstrations where you can induce changes in the brain in terms of plasticity changes, more area given to, say, the rubber hand or something like that from this experience, even though your own, you know, body isn't being directly stimulated, you know, depending on how it's set up. Okay, so it is related to that. However, I'm going to talk about some other examples. And that second image you see there down is somebody performing something called Tai Chi. Maybe you guys know a little bit about this. Tai Chi is a martial art, but it's not, you know, one where you're interacting with somebody else. You're not like, you know, trying to, you know, get them on the ground or fighting or anything like that. It is somewhere between, you know, like a maybe judo and ballet, where really what you're doing is concentrating on the precision of movements. And it's terrific. I see people in the park sometimes doing this. You see them on commercials, typically for Cialis or something like that. You see, you know, a bunch of older folks doing these kind of, you know, I don't know, slow kind of ballet-like motions. My parents did it when they were older. They loved it. They thought it really, really helped. It does seem to help with balance, right? We talked about that being an issue for older folks. It does seem to help with balance. It seems to help with kind of confidence in being able to move, okay? But the part I'm most interested in here is that Tai Chi involves concentration on the fingertips without the fingertips ever touching something. So what they say to do in Tai Chi, for some of the movements, maybe many of them, is to imagine that there's, say, I don't know, extensions out of their fingertips. I think sometimes they'll say, imagine like there's light beams or lasers coming out of each finger, right? And the idea is to make those beams kind of glide over the environment around them as smoothly as possible. Concentrate and imagine those imagined beams coming out of your fingers are slowly painting the scene around you, the trees, okay? I'm in the rain here, right? All the trees around you, or this person in the park. Slowly, make it as precise as possible, as smooth as possible. No jumps, no kind of stops or you know, breaks in the movement. And so they concentrate very hard on their fingertips, even though the fingertips aren't touching. I don't even think many times they're touching, each other, really. A lot of times the fingers are apart. They actually have very little stimulation on the fingertips. However, what it does by concentrating on the fingertips, is it actually enhances their touch sensitivity in their fingertips, which is really interesting, right? So and it really is. It's not like, I'm sure that it's good for them overall. It's good for their bodies, but there seems to be a disproportionate improvement in touch sensitivity to the fingertips themselves. And I think they've done the control conditions where they have people do Tai Chi without concentrating on the fingertips, and it doesn't give the same sensitivity. It doesn't improve the sensitivity as much. And they're measured by how much pressure they need to be able to discriminate between these two grids, the grid going from side to side or the length of the finger. And it absolutely works, which is cool. Again, it's you're not actually going through the physical stimulation of the fingertips, right? Instead, you're going through kind of a mental stimulation of the fingertips where you're concentrating on what the fingers are doing, but trying to be as precise as possible and really paying attention. And if you do that type of mental practice, you see changes in the brain and you see changes in either motor skill or sensitivity to touch in this case. And then I think another really nice example comes from the laboratory. This is kind of a cool experiment. I have a little prop here I can use. And you can see it in this image. Okay. This is an experiment where people put their fingers on a little piece of metal that has 4 holes in it. And so you can see this is what they're doing here. They're just putting it down on a piece of metal, but there's 4 holes. This shows the little holes in the metal here, here, and here. Underneath the holes are little rubber probes, little kind of flexible rubber probes that kind of glide over the fingertips and move in different directions, okay, like this. And that's what this is showing here. And it's kind of the whole thing is run by a computer, but what the person feels is just a little tickle. Can you guys see this okay? Maybe not that well, but imagine a little pick. It's either going this way or that way, but it's happening on all 4 fingers, and it's happening in different patterns, and that's what this is showing. Okay, it's happening in different patterns. Now, the stimulation happens in 2 sets of patterns. What I mean by this is, these are now my probes. I'm not going to use the pick anymore. They go across the fingers at different times. So say I put my fingers on this little grid right here. That's all I'm doing. I'm just kind of not looking at anything. Maybe they blindfold you, maybe they don't. It doesn't make a difference really. But I'm trying to feel the patterns that go across the fingers. These little probes go across the fingers. And it could be something like this, that, first there's one that touches my index finger, and then there's one that touches my pinky, and then there's a probe that touches my ring finger, and then my middle finger. Sometimes it goes the other way. So sometimes the probe will go from back to front, and then the one will go from front to back on the pinky. And so you can imagine it gets a little complicated. It's not just an easy thing where you're being tickled. You have to start trying to recognize the patterns. And so what your job is going to be is one of 2 things. Either you're going to be in the group that's concentrating on the ordering of different fingers being stimulated. And you're going to be told sometimes the stimulation will be from front to back, sometimes it will be from back to front. Don't worry about that. We want you to determine the pattern. Is it pinky first, index finger second, ring finger third, middle finger fourth, or is it something different? We want you to report that to us. Okay, and so people will concentrate on that. Okay, pinky, middle finger, that sort of thing, and they'll say, "Okay, here's what I just experienced," and they'll just do that after a set of 4 things or something like that. Okay, they're concentrating on the stimulation across all fingers. Another group of subjects is going to do this. They're going to get the exact same stimulation, but they're going to be told to concentrate on just one of their fingers. So yes, they do have all 4 fingers touching the thing, right? They say, okay, this time concentrate on your index finger and tell us the pattern. Is it front to back or back to front, and tell us the pattern of those stimulations. So it might be something like this: front to back, back to front, front to back. Okay, and then you report, yep, it was front to back, back to front, okay, that sort of thing. Okay, now concentrate on your middle finger, that index finger again. And they'll do this, even though all 4 of their fingers are being stimulated, they're only told to concentrate on their index finger. And the question is, how does, so yeah, let me get this right. So it's attention to finger touch for the second group. And what it shows is when you then look at the touch strip, remember our favorite strip today, that little band of the brain that's sensitive to touch. If you look to see how it's changed, it will depend on whether you're concentrating on all 4 fingers being stimulated or just 1 finger being stimulated. And you can imagine what happens if you're just attending to your index finger, because that's what the task does. Even though your 4 fingers are being stimulated in the exact same way, the area of devoted to your index finger will get larger. Okay. Versus if you're in the other group and you're attending to all 4 fingers and the pattern that's being presented to all 4 fingers, what is it, pinky first, index first, that sort of thing, your area devoted to those 4 fingers will expand. So the way your brain changes, the plasticity in your brain depends on what you're concentrating on, even if the stimulation is the same in both cases. Okay. Again, neuroplasticity depends on what you think, meaning it's what you're attending to, okay, what you're intensively thinking about. It induces neuroplasticity even in the touch areas of the brain, okay, and motor areas of the brain, depending on how you're concentrating, what you're thinking about. Cool. All right. That is going to have a practical implication for what we're going to talk about in our last slide, having to do with plasticity in touch. Because we're going to talk about maybe something you've heard about before, which has to do with people who've had amputations. I happened to be, I was friends with a physician who works with amputees. And I told him, about the book, and I was talking about this, kind of imagining and the neuroplasticity that's involved with imagining and all that sort of stuff. He said, well, you should come and talk to some of my patients, because this is very relevant to what happens with them when they have an amputation. And so I did. I met with an individual who had just had his lower leg amputated, I guess 2 or 3 weeks earlier before I met him. He was still in the hospital. His name was Ben Curry, and he had his left leg amputated below his knee. It's tough. It is a really tough experience, and he was very generous in sharing his experience with me. People who lose a limb from, in any way, it's a real loss. It's like a mourning. It's absolutely, he told me, he said, I've lost my mom recently. I lost my brother a few years ago. But the, kind of mourning, the sadness he felt about his amputation was stronger and deeper and very, very surprising in some ways, he said. But, he was making the best of it. And he told me what his experience was like, which was, very, very gracious of him, I thought. I knew he had some of this experience. He said that after he had his lower leg amputated, he would sometimes experience a little pain in what seemed to be a location where his foot was. His foot was gone, but he sometimes had a little pain where his toe used to be. Okay? And that's called phantom pain. Maybe you've heard about this sort of thing, phantom pain, where somebody's had an amputation in a limb and they're still feeling something going on in the limb they no longer have. This started to occur about 2 weeks after his amputation. It didn't happen right away. It took some time to just recover, but he started to feel this 2 weeks after the amputation. And he had been primed for this, which didn't always happen. He was told that it was likely if he didn't have pain, he would might have sensation, and then was told the reason why science now thinks this occurs, which is good, because in the old days they didn't know, and the answers they came up with in some ways might have not have always served the patients well. I'll talk about it in a second. Let's talk about Ben though. So he would have pain in his lower toe, or where his lower toe had been, his toe had been, on his left leg. And interestingly, when people have this sort of experience of pain, it often is in a location where, if there was an injury, that's where that's where it would be. And in fact, in Ben's case, that's exactly what happened. He had pretty severe diabetes, and so couldn't feel very much down in his feet at all, and ended up with a terrible infection. By the time he really noticed how serious it was, they realized they had to amputate. But he had eventually had he had damage there where his toe was because of the infection, and that's where his phantom pain was now. And so what he was told, and what he did, is that whenever this happened, he would, whenever he felt pain down there, he would reach down to that position, which no longer had the limb down there. Basically, he's reaching down to empty space, to the air, and start just massaging there in the air, knowing that his toe's not there, it's empty space. But he would massage down there, and he said in some ways it helped. And it's interesting because he was told that this helps a lot of people that have these sorts of pain. And the way he said it was just so brilliant. He said that what I'm doing is I'm kind of scratching down there, I'm massaging, I'm kind of comforting, like to patronize my brain. Like my brain hasn't yet kind of gotten used to the fact that I've lost this much of my body. And by doing this, it's kind of like the rubber hand illusion in a way. It's kind of allowing the brain to kind of imagine that the limb is there. Not consciously. Of course, he knows consciously it's not there, but his touch areas might be kind of comforted in a way. And he was told to do this, and he was told that this does work for a lot of people, which is really interesting. Now, I didn't know this when I was reading about all this work, reading about the case studies, reading about the type of therapies that are used for individuals who have amputations. But fortunately, a lot of people. I guess it's bad for any percentage of people, but I can't remember. It's like 20 or 30% actually have some pain down, in a limb that they've lost. But I didn't know this, that even if you don't have pain, if you lose a limb, you'll have a likely sensation down there. And that's true of 90% of amputees. When they lose their limb, they still have like tinglings in their feet, or a tickling sensation in their leg or their hand if they've lost that. And it's not painful, but it can be a little upsetting, as you can imagine. Your body's reminding you that you've lost something, and it takes some time to get used to as well. In Ben's case, it was even more unpleasant because he had a little pain of that. Now, in the old days, it's interesting. In the old days, when this type of thing happened, so say we're talking 15, 20 years ago, what they would do typically is one of two things, sometimes both actually. They would assume that there must have been some damage where they actually did the incision to remove the limb. And so they assumed that there was some nerve damage there, and they would sometimes resever the nerves there to see if that would help. So they'd go back and do a little surgery to kind of clean things up with the nerves where the incision had been made to remove the limb. Also, and this was often what was thought to be the reason people had phantom sensation or phantom pain, was because of the emotional trauma. And the emotional trauma is very real. It is like losing a loved one, and maybe even more profound as it was in Ben's case. It's very real. But the idea that might be causing the phantom sensation or the phantom pain, I'm not sure was always the best thing to tell a patient, especially since I think now we know it's not true. Okay, yes, the emotional trauma is true. The phantom pain and phantom sensation is true, but the idea that the emotional trauma is what's causing this. So, if we take care of your emotional trauma, you'll no longer feel the sensation, you no longer feel the pain. You might not notice it as much, you might be able to distract yourself more, but it's still going to be there. Because what is probably going on, I think what now most physicians, most scientists think, is that when you lose a limb, plasticity goes crazy. It's called sometimes overexuberant plasticity, neuroplasticity. So, as I said, there's this map, both for touch and for your motor system that maps onto body parts. That map can change pretty readily, as we learned, right? It can change just with practicing keyboard patterns for a few hours and that sort of thing, right? It's a pretty flexible map, pretty sensitive map. When one loses a limb, that map really doesn't know what to do. And that kind of the changes that go on with the map are predictive of how much pain or how much sensation one will have. I've got to be honest here. I don't know if they really know how the connection works, but they do know this. They know that if they do a brain scan and they see a lot of reorganization after the limb is removed, right? So imagine, Ben loses his lower leg. Where's that mapped here? I guess somewhere around here. Okay. Probably in Ben's case, I don't know Ben's particular data on this, but in Ben's case, there was probably a lot of shifting around there after he lost his limb. Maybe that part of his brain map then got dedicated to another part of his body or something like that. Because the more change you see, the more reorganization you see in that map, the more pain and sensation, strong sensation the patient is likely to have. If you see, less reorganization, right? Maybe things kind of creep in slowly. The patient typically has less pain and have less sensation there, which is interesting. The other thing that they'll notice is it depends on which part of the body kind of takes over that space when the amputation occurs. So if you look carefully here, you can see this is how the hand is mapped. It's mapped somewhere here in the brain, all right? Cool. If one loses their hand, okay, in an accident and some sort of, because it has to be removed for whatever reason, and what comes over to take over that area is the arm, okay, the arm being touched, then now fires off cells where the hand map used to be. If that happens, then because it's a nearby body part, it's less likely to involve a lot of phantom pain or strong sensation. If, on the other hand, what takes over from this vacant spot now isn't the arm, but the face, you see how that could happen too, right? The face is right by that area and the face is going to say, well, it's not using that area, so I'm going to come over and kind of map myself onto that. Because the body part that's been removed is further from the body part that's taking over, the face, there's more likely to be a strong phantom sensation and a strong phantom pain. So distant body parts will, in fact, if it's taking over on the map, will induce more pain. Okay, so they know a lot more now, and they know it's not the emotional trauma that's causing the pain. It's what's going on with plasticity. Plasticity, it's typically we've been talking about it as a very positive thing. When you become an expert, you have this plasticity, but it can also be a little harmful. Cool. One more thing I wanted to say, and then we'll do our last question. There have been studies looking at ways to basically do this, apply this patronize the brain thing more formally. And that has to do with treatments that involve using things like mirrors. So imagine, this isn't actually a great photo here because this person, it looks like he has both of his hands intact. Yes, he does. But imagine he doesn't have a left hand that's been amputated. The idea would be this: if his right hand could be put in a box so that its reflection looks like his left hand, and then he can move his right hand in a way that makes it look like he's moving his removed left hand, that can help with certain types of pain as well. And again, this is how it's clearly related to the rubber hand illusion in this case. And there's other examples like this where if you can allow the patient to imagine things about their missing limb and then have that missing limb kind of go through different sorts of movements and things like that, that seems to be helpful too. It's a short-term sort of effect, but in serious cases, it can be done every day, every other day, every week or something like that. Okay. Seems to help, at least last time I looked at that literature. Cool. That ends this part of the discussion on touch. Let's do one more polling question, and we'll finish up. This question has to do with our tongue electrode. Okay, this one should be pretty straightforward for you. Having pattern electrode activity on your tongue with the tongue display unit, A, allows you to perceive lines and curves of various orientations. B, allows you to experience perceived objects outside the body instead on the tongue after some practice. C, induces activity in visual brain regions after some practice. Or D, all of the above. I think this should be very easy for you. Okay, give you about another 20 seconds here. That it? Just 2 people are responding. 6 participants. 2 people. Okay, 3. Thank you. That should do it. Let's end there. Let me give you the answer since I want to make sure we finish on time here. The correct answer, as you all thought, or the 3 of you that responded thought, is in fact D. It can, at least at first, allow you to perceive lines and curves, but then with practice, you start to feel like things are outside your body. And when that occurs, it seems to start making use of your visual brain areas. So it is all 3 are true, so the correct answer in this case would be D. Terrific. Go ahead and take your picture, and we will see you on Thursday. Bye-bye.